So the next talk is going to be Dana Hurley, who's going to be presenting on modeling analysis of mobile hydration on the moon. Okay. Can we start at the beginning, please? Thank you. All right, so yeah, we're going to be talking about modeling the idea of mobile hydration on the surface of the moon. And the phenomenon that we're trying to understand is these observations from M-cubed and LAMP and other instruments that seem to indicate that there is some diurnal signal of hydration on the day side of the moon. And this is a LAMP image here, or not image, but LAMP data here that show as a function of time of day and latitude that there is a change in the amount of hydration on the surface of the moon. So high is more hydration, and down here is less hydration, and each different color is a different latitude band. And in the middle here is noontime. And so you can see as you go from morning to noon, you lose hydration at all latitudes, and then you build it back up after noon. And the amount of hydration is separated as a function of latitude. So there are lots of data that are consistent with this. And so there is some sort of diurnal signal in the data. But what we don't understand is whether or not this local and latitudinal distribution means that there is actually a mobile component of hydration. Another alternative could be that it's produced and lost in place, and it's just a change in the steady state balance as a function of local time and latitude. What we also don't know is some observations may be consistent with there being a significant reservoir at dawn, but those are inconclusive at the moment. And there may be, there are observations that there's a lack of a steady background water exosphere of the moon, which suggests that there isn't water hopping around on the moon. So we want to try to bring some of these disparate observations together through modeling of water migrating on the moon. And yeah, so. Did I do something? Oh, that's power, isn't it? Uh-huh. Okay. All right, so my model is a time-dependent exosphere model, and I use two different sources of water. One is meteoroids, and those are concentrated at the dawn terminator, and I use a thermal distribution at 3,000 Kelvin. I also model a solar wind source, where it's a dayside source, and the temperature is at the surface temperature, so we're assuming it's a chemical sputtering. And in the model, I use the cold traps to permanently trap any water that gets to them, and they're added in statistically, just using the fractional area of the cold traps as a function of latitude from Erwin Mazurico. The distribution of activation energies used in the model represent or gives various strength of absorption sites, and that's something that I can vary in the model. There's also a finite chance of non-thermal loss, and then any particle that gets re-released after it comes in contact with the surface gets re-released with the velocity taken from the local Maxwell-Boltzmann distribution. So the model keeps track of where all of these particles go. The source brings them in, and then it tracks them as a function of time, and it keeps track of the particles that are off of the surface, so they're in the exosphere, and so we can get a map of the exospheric density, and we also can keep track of any particles that's stuck on the surface, so we can get a map of the surface density. Okay, so for the particles that are on the surface, we can break those up into two different kinds of particles that are on the surface. One is a water molecule that's come into contact with the surface, and I know because my model's doing the calculation whether that molecule is eventually going to desorb later on, or if it's at some location where it's stuck and it's never going to see the temperature it needs to desorb. So the particles that will eventually desorb again, I call those the migrating particles, and those are particles that are going to appear as the diurnal signal, right? If something's permanently stuck, it's going to be part of a background that's not going to change, but if it's actually going to desorb, it's part of that diurnal signal. So here are two different models. This one's using the meteoroid source, and this one over here is using the solar wind source of the particles that are on the surface but are still available to migrate. And you can see from these maps where 0 is noon and minus 90 is the dawn terminator and plus 90 is the evening terminator, that in both of these models you get a significant buildup on the dawn side. You lose hydration during the hot parts of the day, and then you start to reaccumulate it at night. The reason why these two look so different is because the meteoroid source is centered on the morning hemisphere. So, and then the solar wind source is centered at noon. So the difference between the two is particles that are very recently released. So they haven't lost track of what their source was yet. Okay, so if we look at that as a function of longitude, again, 0's at noon, and latitude bands, you can see that you can get the sort of bite out at noon as has been observed in the data sets. There is this asymmetry, though. If you take this here that has the morning on this side and the afternoon on this side, and you fold it back on itself, you can see there's this great asymmetry between the morning and afternoon hemispheres, which does not seem to be consistent with what's been observed. We can also look at the particles in the model that have stuck or hit the surface and they're on a spot where they're never going to leave. And you get this is how you get a latitudinal offset. So you get higher densities at the higher latitudes of particles that are on the surface that are forming a background. In the model, I can use different sticking parameters, and you get different latitudinal distributions depending on what those choices are. Maybe. Can I get next slide, please? Thank you. So if you're observing from an orbiting satellite or something like that, and you're looking at what hydration is on the surface, what you're going to see is the combination of those particles that are permanently stuck forming the background and the particles that are migrating. And when you combine those two in the model, you can reproduce something that looks pretty much like what's been observed, where you have this offset in latitude, the high latitudes having higher amounts of surface hydration, the lower latitudes having less, and then this bite out at noon. Because the model just assumes that particles that when they hit some site are permanently stuck, they don't go away, but obviously so that's not really happening on the moon, or otherwise we'd get this continual buildup of hydration, and that is not occurring. So basically, when I combine it for about, when I say those particles that are permanently stuck, if they have a lifetime of about 20 lunations and an offset as a function of latitude, you get a nice combination of the two. So that was the meteoroid source. If you look at the solar wind source, you get a very similar situation. Here we use 50 lunations for the amount of time that one of those long-term sticking things lasts. And with the solar wind source, you don't have quite the same asymmetry from the dawn to dusk side as you do with the meteoroid source. So then if we look at the exospheric contents, again, 0 here is noon, that's dawn, and that's dusk. So with the meteoroid source, you have a lot of water in the exosphere on the morning side, but not on the afternoon side. With the solar wind source, it's a little bit more centered, but still offset toward the dawn side. But we can relate the amount of water that would be in the exosphere to the amount that's moving around on the surface. And this is kind of the number that you need to work with if you are trying to relate these things. If you have an exospheric density of about 100 per cc, then it would correspond to a surface density of about 10 to the 11 per centimeter squared. So if we look at that ratio as a function of latitude, you can see it somewhere on, but instead of looking at the exospheric densities and volume, we're looking at the integrated column density, so it's again in a per centimeter squared. It's a factor of about 100 between the amount that's on the surface and the amount that's in the exosphere. So LADEE has observed water in the exosphere of the moon, and these are the LADEE observations as a function of local time. So 12 here is noon, and 6 here is dawn, that's dusk. The color code is the altitude at which the measurement was obtained, and the bottom line of this figure is that there is no organization of water in the exosphere of the moon as a function of altitude or local time. That is obvious to me. But what we could do is reproduce this stochastic signal based on water being delivered by meteoroids. And what you're actually witnessing is not the background exosphere coming from meteoroids, but individual vapor plumes that we're flying through. So if we superpose our model exosphere from the meteoroid source, if those vapor plumes then continue to migrate on, you would have a background exosphere like this, and with all these data points below that, that suggests that water that's being delivered by micrometeoroids is not then migrating around. And next, please. Here is the model of the exosphere with the solar wind as the source, and again, all these data points are below the model, which suggests that solar wind is not very efficient at producing water that would then migrate around. Next, please. Oh, there we go. All right, so in conclusion, sticking on the surface of water molecules can produce a local time and a latitudinal variation in hydration on the moon. And the models that I'm using show that it's asymmetric around noon, has maximum near dawn on the morning side, and that long-term sticking is needed to reproduce any latitudinal effect. And then if you have hydration that is mobile through the exosphere, that's going to imply some amount of water that's in the exosphere. And based on our LADEE measurements, we can constrain that source rate to less than 0.02 grams per second of water that's actually migrating through the exosphere. So, thank you.